Hi and good morning, and welcome to this morning's webinar in association with the IHEAM monthly magazine Health Estate Journal, of which I'm the editor. The title of the webinar is Critical Ventilation, Validation and Sustainability Strategy, Considerations for Construction, Handover and Clinical Use, and it will be presented by Howarth's Service and After Sales Technical Manager, Mike Dunn. Among the topics Mike is going to cover will be ventilation system design and commissioning for validation in accordance with HTM 0301 Part A and BSRIA BG 49 2015, air handling units and what options are available, room pressures and air change rates, including a look at what tests should be carried out and the calculations behind air change rates, the importance of getting validation right and why ventilation is so important in healthcare, and sustainability and control strategy for healthcare installations. Howarth says, throughout 2023, Howarth Air Technology saw a significant increase in requests for expertise in critical ventilation systems from right across the health sector. 2023 was also the year we held the highest attended HEJ webinar, and with the feedback from that session, plus the professional experiences from the last calendar year, we're back again to take an in-depth look at the key ventilation issues in healthcare settings. Mike Dunn, who presents this morning, graduated with a first-class honours Building Services and Sustainable Engineering degree last summer. He's a fellow of IHEAM, contributor to HTM03 and a member of multiple engineering institutes, and he heads up the technical validation team at Howarth. If you have any questions as the webinar progresses, please type them into the panel on the right of your screen. And at the end of the presentation, Mike will answer as many of the questions as time allows. We have had some great questions in previous Howarth webinars. I'm sure you'll find this an informative and valuable session, and thank you for attending. Over to you, Mike.
Thank you, Jonathan. So good morning, everyone. I'm just going to turn my camera off so that I can present to you. And we should be ready to go. So good morning. As Jonathan said, my name is Mike. I'm the Technical Manager in the Service and After Sales Division at Howarth Air Technology. Thank you for joining me this morning. We've got 42 slides that we're going to get through covering the topics that Jonathan's already sort of touched on. But these are all topics that I'm quite passionate about. And hopefully by the end of it, you will have some sort of understanding or a better understanding of the requirements that we need to try and tick off to get these systems into better use within our healthcare buildings across the UK. So again, as Jonathan's already touched on, these are the sort of specific topics we're going to look at, paying particular focus to the guidance and the legislation around design and commissioning, the specifics of air handling units and why they're so important within healthcare and how they can cause us problems, and the areas that should be captured early within the validation or design of a process. Room pressures and air change rates within an operating theatre and how we're going to tie the documentation together between health technical memorandums and health building notes. The importance of ventilation in healthcare and why we do it, why we go to this length and what we're trying to achieve. And then something that I'm massively passionate about at the end, sustainability and control strategy within healthcare, because without that, we're not going to achieve the goals of net zero. So when I was first collating these slides, I was trying to figure out a way that I could sort of almost get the message across to you in a systematic way that enabled everybody to understand where we would be at various processes. So in my logical mind, the first place to start was with the REVA Plan of Works. And there's various places that we're going to look at. And obviously I'm sat here with Howarth Air Technology in the bottom right hand corner of the slides. So I do work for a manufacturer, but I don't want to talk to you today as a manufacturer. I want to talk to you about someone who has the experiences of everything and the pain that we've been through on some occasions. We're trying to get technical capabilities out into the operating theatres or clinical spaces that we're dealing with. However, from a manufacturer's point of view, it is really important, and it doesn't matter if it's a UCV canopy, the air handling unit, a chiller plant, whatever it might be, you need to engage with the manufacturers early within the process of the whole plan of work around the process of installing a new operating theatre, all the way up to potentially building a new hospital. I've always found that early engagement with manufacturers is a real key element, particularly when things get quite complex in a barn theatre, for example. However, we're going to talk about validation today. So again, validators or the authorising engineer for VENT, they need to be involved with the process early in the early stages, in the briefing, the preparation of the system and the collation of the scopes, so we can move through the later stages of the REBA plan. And then obviously the ventilation safety group, they will also be part of every single stage, but they further, the authorising engineer for vent would be part of that safety group, but then they go on from handover and then into clinical use. And the reason that I put clinical pack there, complete pack there below the ventilation safety group is because I've seen systems where it's just been commissioned and not independently validated afterwards. Then it goes into clinical use with issues then from a mechanical point of view later down the line. So it's got to be a complete holistic approach and look at the system. So ventilation system design commissioning then, and the documentation that we're going to use around this that I'm going to talk about for people that may not be familiar with it on the webinar is HTML 301 Part A, which is all about design, validation, and the requirements from sort of new installations of ventilation systems. We may touch on HTML 3 Part B, which is the operational management of systems. However, it does have in Chapter 3 a really, really good checklist for minimum standards that we include in our validations, which I think not every validator does, but it's a really good like aid memoir to make sure that we tick all the boxes. And then later in the slides, I'm going to touch on HBN 26 to keep the theme around operating theatres. HBN 26, for those of you who don't know, is a health building note. There's lots of different health building notes, like there's lots of different HTMs. We have HBN 04 for isolation rooms, HBN 06 for imaging suites. But today we're going to focus on HBN 26, and I'm going to show you how the calculations tie together with the actual architectural size of the room. So the documents that I want you all to be aware of, and maybe if there's something that you're going to take out of this webinar, then go away and have a look at these documents. The first one is BSRIA BG49. It's a key document that we use in all our validations, and it's something that I cite a lot within my work. CIBSE Commissioning Codes of Practice is a big one in the industry. Ventilation and ductwork Guide B2, and then we have DW144 and DW143 from BSRIA. Now these two documents are for the installation of ductwork and ductwork pressure testing of the system. So they're also really important documents that we're going to touch on today. But the one we're going to focus on is BG49. Now, from a designer's point of view, in those early stages of REBA, I think these are the 4 areas that we sort of need to consider. Obviously, there's a lot of things you need to consider, and this is a very sort of broad brush approach. But if I just take you through these 4 areas, we've got the first area is an assessment of the system, which must happen in the early stages of REBA. I've put about a clear defined agreed derogation register right at the start of the process. However, I did take some advice on this from the head of construction at Procure 23 when I was collating these slides. And she said that no derogations are acceptable, which I agree with. But when we're going into existing hospitals and putting in the operating theatre in, we may have constraints from very old designs of the building, and obviously that then has to go into a derogation. To get derogation through, it's very complex, and it goes all the way through the NHS up to the chief executive. There's very, very in-depth guidance in this document here, which is what my colleague told me to quote and reference. So if anybody is on the call today and they get involved with derogations or early stages of design, then just take a note of that, go away from the webinar, download that document. It's there's a lot more detail in that than there is in this presentation on derogations, but it's something that you need to be aware of. The location of plant and duct runs is obviously an important one. In the early stages when the Revit models are being created, obviously we can size and adequately place ductwork. We're going to speak about that in a moment. But it's important that those early stages that the designer appreciates what's required within the ductwork. We have to put test positions in, which I'm going to show you in the next couple of slides. Those test positions must be repeatable, robust, and there must be a method of calibration if we're going to use something automated like a DPM, which again, I'm going to show you in a couple of slides. Ventilation noise or system noise is another big one, not just to the system, but to also our neighbours. We need to attenuate the air handling unit to our neighbours, and we also need to attenuate the ventilation system to the usable space. Obviously, there's design requirements from noise in CIBSE Guide A for normal general environments, but there is in HTML3 as well for clinical environments. And it's not acceptable if a designer has missed off a VCD to balance a low-level extract on an opposed blade damper, for example, within an operating theatre. That's just going to send the noise level straight through the roof. We need an adequate place VCD further downstream from the diffuser, and adequate places to test that as well. And then finally, the system must be annually managed in healthcare. Obviously, we have Part B that tells us that. And every 10 years in healthcare, we need to break those components up within the air handling unit, within the ventilation system, and maybe replace them. And that could be 3-port valves. We may want to nitrogen clean the coils. We may want to do something with the drip trays, might be corroding. So we need to have enough space around the air handling unit to get those bits and pieces out when we're actually going to come and do that. I validated air handling units where the fog coil on the front of the air handling unit wouldn't come out. It was stuck in between a riser and another air handling unit, and that system was accepted. But that should have been picked up early and adequately assessed through the derogation or whatever it might have been. But there was no process in place to get that out if it was to burst. So keeping in line with the ventilation design then, this is an extract from BG49. And for those of us on the call that may be familiar with measuring a velocity within in a duct, there's a requirement that those test positions, when we drill into the ducts and put our pitot traverse in, so we can use a micromanometer and measure the velocity, must be 10 times the diameter of the duct off the bend. So you can see in this instance 10 times the diameter of the duct to put an adequate test position to enable the air to become more laminar so we can get a reading on it. One of the first things that I do as a project is reaching validation stage and completion is ask for the commissioning data of the system. And you can tell usually from looking over the pitot traverse readings and static pressures if the test position is in an adequate position. Now, the responsibility doesn't necessarily all dump on the designer in BG49 because it does say preferably with the help of a commissioning specialist. And that would be someone from like Ashford's or Barnyards or one of the big end systems, one of the big commissioning companies, or the commissioning engineer who's au fait with the system, because you can see that the diameter of the duct changes with different parts that are in the system. So we've got a butterfly damper, a battery or a filter, an axial fan or a centrifugal fan within the system. It just changes that distance. So it's something that we need to be aware of and something that we need to know. And this is some examples that I've seen whilst I've been out on site. And you can this is a CMRP sensor. They're not very popular, but there is quite a few of them out in the industry. And basically the way that they work is they sit with on the air handling unit somewhere, and you can see these sort of lances that sit with inside the ductwork, measures a pressure, and it turns that into a velocity. So you can see this reading out here is got 1.265 meters cubed per second, or 1,265 liters flowing through it. And they also read a pressure as well, because everything that indicates a flow rate starts with a pressure. So you can see it's taking a velocity and static pressure. There's also a Wilson flow grid that works in a similar fashion, and you can see if you're familiar with pitot traversing, you can see that it has these sensors across the duct, and it's reading a pressure and turning it into a velocity through some sort of sensor. And then I thought I'd add in this bottom tile as well. This is a Corex honeycomb, and for those of you on the call that may have sit the authorised person of event course at Eastwood Park, this is something that the tutor on that course recommends. Never really seen it in practice, but I'm told that it reduces the 10D values by about half, so to 5 times the diameter of the ducts. Have seen it in practice with Zeal. I was talking to them last week about an axial fan for an air handling unit, and they put a Corex honeycomb across the intake section of the fan, and they believe that it makes it more laminar and takes some design noise out of the fan. So that it is in use. I've just never seen it in use inside the duct, but I thought I'd mention it because it's on that course. So keeping in mind the 10 times of the diameter of the ducts and making sure that the air is laminar to make an adequate traverse and calculation of an air change rate or a total volume of an air handling unit. Probably the most complex arrangement that we'll get in a UCV operating theatre is the UCV. The ductwork configuration can at times be significantly different to a conventional operating theatre or a recovery suite or whatever it might be. And the reason is this. So in the UK, we have 2 options. We have a modular or remote type UCV. 98% of the canopies that Haworth sell are a modular type unit. And then these sort of canopies you may see with knocking about the industry would be called a flush type canopy. You'd see it flush within the ceiling. Now, the benefit of having this type of system is you can take a pitot traverse here to get the total volume to the operating theatre. So that can be used for the air change rate calculation, which I'm going to touch on later on with you all. And then if we had adequate length from there to the intake section here where it comes onto the UCV, we could take a traverse there, a traverse there, a traverse there, and a traverse there, and then we could get a total volume then to each quarter to balance the ventilation system to the UCV2. You can see that there's VCDs at each leg, so the system can be quite easily worked on, balanced and assessed from a clinical and an engineering point of view. Now, the other side of these remote systems here that you can see, they work in a similar fashion. The only difference is they don't have these fans that sit within the operating theatre. Usually it's taken from an air handling unit, and the fan does the recirc for the UCV. Now, an important point with these UCVs is the supplier that comes from the air handling unit obviously gives the room pressure, gives the temperature control, the humidity control to the air, but it works in a recirculating fashion. So under the footprint of a UCV, you will have 500 air changes an hour. 33% of those air changes come from the ventilation system. 66% of the air changes come from the recirculating fashion of a UCV canopy. That's just the way that it works. So if you keep that in mind, obviously we've got the 10 times the diameter of the duct off the bend, so it'd be very difficult to take a traverse on that type of ductwork arrangement. And also you have the issue of measuring the recirc air. So these are low-level extracts from the operating theatre. These feed back into the system. There's additional components up there. We've got an attenuator, a cooling coil, the filtration sits above the canopy. And the reason that I'm showing you this is because you need to be aware of that when you're designing the ventilation system. You need to consider how you're going to get traverse to it, how we're going to clinically work out the air change rate for the operating theatre, and make sure that it's adequate and repeatable. So to mitigate that issue then, this is the way that a ductwork configuration or an ideal ductwork configuration can be put together. So we have the modular type of canopy on this drawing here, so you can see that there. And the way that it's looked at, or the way that it's going to be measured, is that there's a drop within the plant room from this ductwork here. The ductwork comes down in this fashion, and then it splits to leg 1 and leg 2. So we have a VCD there for leg 1 and a VCD there for leg 2, which is fine. And then if you were to put a mirror down the center of the canopy, you've almost got complete symmetry, with the exception of this coming in at the center. You can see that these ductwork connections here are the same at the top and the bottom, and you have VCDs for then each position at each corner of the ventilation system. So we could take a total traverse within the operating theatre, within the plant room upstairs, to calculate for the operating theatre. And then another thing that you can get within UCV operating theatres is the canopy having an impact on the rest of the ventilation system. So we mitigate that by taking the other areas. This has got a recovery, some prep rooms, and anaesthetic. They're all on different drops, as far away from the UCV as possible. So that's one way of doing it. Another way to do it is to bring cylindrical duct straight to the back of the fan. You can see here we've got, this was a project I worked on a long time ago at Haworth. We have the ductwork that's sort of shot across the top of the plant room, and then it dropped equally. Symmetry is the key at each corner of the UCV. You can see we've got a VCD access panel, so you can get in and check that, and we could drill, take our traverses. We could even balance it on pressure. The system was that symmetrical. And obviously there's other bits and pieces within the industry that we can look at, and there's new stuff coming into the industry all the time, and this is a fairly new method of assessing a flow rate coming down an air handling unit. Obviously, I'm guessing that most people on the call would be familiar with fan curves and assessments of fan curves within centrifugal fans or axial fans, whatever it might be. But these are the type of fans that we have now within air handling units. We have a plug fan, we have an EC fan. The EC stands for electronically communicated. Within the fan, you can see here that's the motor, and the impeller sits on this side. This has a driver that's connected, and I'll talk to you more about EC fans later in the slides, but there's a driver connected there to the impeller, and then there's a pressure loop that sits on this side of the fan. We can connect a micromanometer across that to get a delta P, or a difference in pressure. We take that difference in pressure, multiply that by the K factor that is given on the side of the fan, and then that will give you a flow rate in meters cubed per hour. So at the bottom here, I've just given you an example of one of the engineers that we've carried out on one of the validations, because we couldn't get an adequate test position. And this is what we've done. We've done this exact test that we've got on this slide. The only difference is we've divided it by 3,600 to get the volume back into meters cubed per second. So we can report our values in the same unit within the report. One thing I would notice is I know that this has been going on around the country in various projects, and BSRIA don't see this as an approved method of assessing the volume down the air handling unit, but I think it's important that everybody's aware of it. So we do all that work to get the air through the air handling unit and make sure that it's being delivered where we want it to be delivered. But there's 3 steps that need to also be considered in terms of permeability testing of the air handling unit. So within HTML3, there's a standard that's referenced, BSEN 1886. And these are the stages that it sort of relates to. So the first step, step 1, is the AHU factory pressure test. Now, I'm working on a project at the moment of 2 UCD operating theatres that we're going to validate further down the line. And this step has been omitted by the authorising engineer for Vent, because he's basically said, what's the point in doing that on a factory, then breaking it up and then swinging it onto site through a crane and then redoing the pressure test again? So we could sometimes skip that, but it has to be a discussion with the authorising engineer for Vent on behalf of the customer. Step 2, we get to site, and it's absolutely essential that then the AHU is pressure tested on site. So your manufacturers would do that, AHS or Mansfield Pollard or whoever it may be, it would offer that service or could potentially offer that service. Once that's adequate, obviously we connect the ductwork up with keeping DW143 and DW144 in our minds. We install the ductwork in accordance with that. And then the ductwork must undergo a pressure test then. 100% of the ductwork must be pressure tested. We don't want to be taking sections of ductwork or leaving existing ductwork half tested and not tested. The full system has got to be tested. If we're starting from scratch, we've got to start at this point. And the classification of that ductwork is Class B. So keeping permeability testing within our mind, obviously we do the mechanical ventilation system, we do the HVAC system, we do the ductwork arrangement in accordance with the visa documents. And then we have to also assess the permeability test of the room. So this is a pressure test of the room, and we're basically checking the fabric and making sure that that room is adequate for the purpose. So when we get to commissioning and validation, we don't want to be struggling to try and get our pressure regime. And one of the questions that we can answer later at this stage is actually the room pressure permeability test passed, so it can't be an issue with the actual fabric of the room. That's where we want to be. The document that I put on the slide there is BTS 3/2018. There is work going on in the background at various societies within the industry around guidance on permeability testing, because at the minute it is a bit sketchy when it comes to operating theatres. But this is sort of how we look at it. The way that we test permeability is we take the operating theatre up to 50 pascals, then measure decay with a pressure limit of 2.5 meters cubed per hour per meter squared at 50 pascals. And then we take the room back, so we put a zip up door. You can see the zip up door on the front cover there. Put the zip up door on, we draw the room back 50 pascals. And the reason we do that is it's challenging different areas of the finish. So we can challenge the windows by taking it up to negative if the windows are adjacent to an outer area, for example, because if you put pressure against a window, that will force it into its seal, and it may give us an inaccurate permeability test. So we take it on both sides at 50 and plus 50 and minus 50. Now, as part of my dissertation, I brought this in, that's a snap from my work, and one of the questions asked was, why is it 50? And the reason that I was told by someone who's pretty au fait with this was the casual pressure on a building, a 3-story building, is 50 pascals, and as the air sweeps over the roof, it can become negative. So that was the rationale behind it whenever that document was put together by people who are much more familiar with that test than I am. But there is some links at the bottoms there that you can follow after the webinar that may give you some guidance further into this. I know the CIBSE Healthcare Group are collating a healthcare document, and I'm almost certain that this will be in it from the chap that's collecting it. So healthcare AHUs and the configuration of those AHUs, then obviously air handling units within healthcare are very specific. It's not a standard building services type arrangement, and these are the reasons why. So we have considerations that we've got to make. There's lots of considerations, but I'll put some like high level ones on this slide before I go into the nuts and bolts of it. So obviously within an air handling unit, any type of pooling water, I'm going to talk about water control in the air handling unit in a moment, is an absolute disaster, because that can be a breeding ground for Legionella. Immunosuppressed patients could be on the other end of our air handling units, and Legionella is a disaster. So we're going to configure the air handling unit in a way that reduces the risk of Legionella. I'm going to explain that in a moment. We've obviously got to carefully consider the location and intake of discharge points on the air handling unit. HTM does say there's a minimum of 4 meters apart, but that's not the only thing that we should be considering. we should be considering the discharge points of other air handling units, LEV systems, helicopter pads, if it's a big acute emergency hospital. Is the intake section of the air handling unit sat in the car park and there's a diesel wagon that comes there every morning for 40 minutes of offloading all the food for the day? These are the things that we need to consider as designers, as validators, as authorized people for Vent. These are really important things that we need to take into account. And then finally, construction work is happening on our sites. We need to take into account where that intake section is, because aspergillus is a risk coming from dust. If we've got a construction going on site, which may be knocking down a multi-story car park, for example, and we've got an air handling unit that's right across the way, and it's supplying the air into an intensive care unit or a high dependency unit or a special care baby unit. These are the things that we need to consider, and if there is a risk, it's up to the ventilation safety group, the authorising engineer to Vent, to help them come up with a solution to mitigate the problem. So if you guys go away from here today and you look into the documentation, you're going to see some strange numbers within the document that relate to filter classification. So again, I've taken this from the Specialist Ventilation and Healthcare Society. This was something that their team put together in 2018. And a lot of you may be familiar with the G4, F7, F9 type arrangement, but now you can see that those classifications have been broken up into a much more detailed classification parameter list, which is all sort of based around the outside air quality as well. So if you go back and you see an ISO EPM 165%, you know that the classification is around that figure. But I just put that in there. These slides will be made available for everyone at the end of the presentation. It's there as an aid memoir for people who come, and it just gets you thinking, and you can move away and do your own research around that BSEN 16798 regulation, and hopefully it's of some use. So the air handling unit then, and the way that we're going to look at it, we're going to obviously start with these ancillary bits and pieces that are in the air handling unit. So we're going to talk about water again in a minute, but the water sort of is the way that we assess the water, I think, is a better way of explaining it from a management point of view, and a validation point of view, is looking at these type of traps here. It's got a glass trap. You can see here, you'll have seen them on your sites and on your designs. That's what they look like. But the reason that I put it on from a validation point of view is because they are directional and they've got to go in a certain direction. This side of the trap here will go to a copper drain, which will be at a certain degree slant. There's got to be a 15 mil air gap. These are the type of things that we're checking and we're making sure that are in position. The water that sits in the trap as well is an indicator of how the AHU is performing. So one that you may frequently see is black water, general dirt coming through the air handling unit, could indicate filter failure. If there's an old air handling unit with belts inside there, that could be a sign that the belts are starting to corrode or need to be replaced. And obviously the other bits and pieces that come to some really nasty microbiological issues that obviously need to be addressed. Within the air handling unit, this is a massive air handling unit. It's not a clinical grade one, but you would maybe see 4 of these within an air handling unit or 2. And this is an EC fan and an electronic communicated fan. This is the driver on the back of the fan here. And inside the driver, you would have an AC voltage, be it single phase or 3 phase. And then you would have a control cable as well, or a control loom. Within that control loom, we would have a ground, a 0 to 10 volt in, a plus 10 volt, and a tacho. And we can use that information to do different types of things with the fan. There's a controller here that I've dropped in again from Zeal, so you just get a bit of an idea of what the controllers would look like. And the benefit of these is we can sort of reduce the risk. There's a redundancy risk argument that could be had. So if one fan comes out or fails, the other fan must achieve 80% of the flow rate through the air handling unit. We get better heat transfer with these type of fan walls, better movement of air down the air handling unit. So these are they're a really good thing. I think they're going to become quite popular, I believe. So onto the air handling units then. So there's 4 options within HTM. And this method that I've got in front of you now is the least efficient method of heat recovery within the availability of the marketplace. If we go from left to right across the air handling unit, you can see that there's attenuation to our neighbours. As I mentioned before, sound management is important, and attenuation to the system. So we need to consider that when we're putting in test positions for the total traverse. Obviously, we can't drill into an attenuator. We just need to consider that as a designer. There's motorised dampers that sit at each end of the air handling unit, and you'll notice now that this is a fog coil, not a frost coil. So the fog coil's duty or job there is to, firstly, not be finned, because you can see that it's unfiltered, so we want it to be quite an open space. But it's there just to take the air above dew point. So we don't want the outside air getting the primary filter wet, and that's the reason, or damp. That's the reason that the fog coil is there. The warmer this fog coil goes, the less efficient the heat recovery section is on any type of air handling unit. So it gives a value of 2K within HTM, and then again, that's the designer's responsibility to look at that. And then working left to right, like I've said, we look at the supply air handling unit that sits in the middle. We've got the supply fan here. This is on negative pressure, that's under positive pressure. So as we move air this way, everything this side of the fan is under positive pressure. The runaround coil works like this. We have a coil that sits in the supply system and a coil that sits in the extract system. A fluid moves between the two, and a pump pumps that fluid round. And basically, obviously, we've got energy to run the pump. There's losses in the system to push the fluid around, so it's not ideal. The cooling coil sits on the discharge side of the fan. Now, there's an important reason for that. We can't have that on the suction side of the fan. We need it on the discharge side of the fan. The eliminator is shown on the drawing for velocities internal of the AHU greater than 2 meters a second. The reason that it's on the positive side of the fan is because of the air hits dew point. We need it to be pushed away and drained into the system. We can't have pooling water this side of the coil or under the coil. It's got to be removed. The heater battery is the final major component, and then we have the filters that sit at the end, which would be to that classification that I showed you on the previous slide. Fire dampers take us through the floor. We have the operating theatre, and then you can see we give a trimmer battery to the layout prep room to offset that. And there's design stuff that you can do with that as well from if it's a UCV operating theatre. Filter classifications are a minimum standard over here. We have EPM 10 50% for the pre, which is this one, and EPM 1 greater than or equal to 80% on the final filter, which is this one. The second option that's been given in HTM from 2021 is a thermal wheel. And the way that a thermal wheel works is basically it moves very slowly between the two return and supply legs. And it's basically recovering energy from the return and putting it back into the supply side to reduce the pressure on the heating coil. You can see that all the components within this are at the bottom of the air handling unit. That's done by design. So if one of these need changing, it's easier to change. There's not as much lifting and shifting for engineers. And an interesting point with the thermal wheel is that we were told to isolate them in COVID by CIBSE, which is the Chartered Institute of Building Service Engineers. And wheel alignment of the wheel can be an issue sometimes as well, which can lead to stagnating water under the wheel. So yeah, just things to consider from a design point of view. Option 3 is the heat plate exchanger. This is probably one of the most common air handling units within healthcare. And again, you can see the components are at low level. The cooling coil is on the discharge side of the fan as the air moves in this direction. And we have 80% efficiency from the heat recovery in these sort of circa. Obviously, we need to make sure that this is a fog, not frost, and that's 2K to the outside to increase that efficiency from the heat plate exchange. A fairly new air handling unit that's in the industry is the cabinet air handling unit. And again, becoming popular. You can see it has the least efficient method of heat recovery, but you can fit sort of 2 of those in the footprint of that roughly. So in terms of refurbishments, they're a good option. And yeah, there's a lot of manufacturers out there doing them now. AHS won an award for this at IHEAM last year, which is an excellent unit. They're all really good. There's some good units knocking about. So yeah, access from an engineering point of view, maintenance, it's all good stuff. Now, we did some training at the start of the year with Siggy Volkman, who's a consultant within our industry, and she brought this slide to us, so I thought it'd be good to drop it in for you guys because I've never seen anything like this before. It's a sustainable heat plate exchange air handling unit. You can see it's got a heat pump on it, and I just thought that as designers, as people who are interested in this industry, I just thought it'd be interesting to know. So I've left that in there for you guys. So room pressures, air change rates, HBNs, HTMs, how do we tie them all together? So without doing a full presentation on health building notes and architectural design of clinical spaces, I just thought I'd take something that was relatively straightforward and easy for me to explain. So if we take a look at HBN 26 at 4.69, it says the standard size of an operating theatre is 55 metres squared. It doesn't give us a height, so it doesn't give us a volume, but let's assume a 3 metre ceiling within the operating theatre. If we have 55 metres squared and a 3 metre ceiling, that gives us a room volume of 165. And then if we do our calculations that I'm going to show you in a couple of slides, so don't worry about how I've come to this conclusion, but we take the room volume, the standard flow rate for a UCV operating theatre from HTML3 from the standard layouts, do our calculation, and the air change rate works out identically to exactly what we're after, 22 air changes. Now, the reason that it's important that you all need to note this and think about it is because you tomorrow might order a UCV canopy from a UCV manufacturer, and they'll give you a minimum supply flow rate to the UCV from the HVAC system. So speaking from how I was in my shoes, our Xflow 28 has a minimum design flow rate of 0.92, 920 litres. Now, that's important to know because if you do the HBN 26 design, you do your 55 metre square, you put 3 metre ceiling in, then you drop our canopy in, you put the design flow rate to the canopy from the manufacturer, you're going to be under your design air change rate. And the reason that we give you this design air change rate here is because we've taken account of all the heat gains and everything that's inside the canopy, taking consideration of sensible latent heat gains that come from the motors, that come from the lighting. And 11 degrees off coil, that will give you something like 18, 19 degrees within the operating theatre. So this is a design flow rate for a building services application. This is a design flow rate to govern the air change rate within the operating theatre. So basically what I'm trying to tell you is make sure you do your calculations and make sure you crunch your figures. Don't just go off the data that's been given to you from manufacturers. Make sure you do your maths and do your homework and make sure you get everything right before it actually gets to site. So talking about site and thinking about the problems that may come across your desk as designers, as appointed people, as ventilation safety groups, these are the two types of main operating theatres that we can get in the UK. We've got a UCV operating theatre on the left, we've got a conventional operating theatre on the right. First thing I need you to notice is UCV operating theatre has a sterile pack store, and the conventional theatre or the general theatre has a layup prep room. Notice that the volumes are significantly different, which I'm not necessarily that bothered about in this presentation, but I need you to notice the pressure between the room. So the pressure is 25 pascals in an SPS to the corridor, it's 25 pascals in the operating theatre to corridor. In a layup prep room, it's 35 pascals to corridor, and it's 25 pascals to corridor in a conventional theatre. So with that in mind, if this is at the same potential or pressure as the operating theatre, this must be a transfer grill. The transfer grill is there to equalise the pressure. And in this instance, the pressure is higher, it's 10 pascals higher, so that must be a pressure stabiliser, which it indicates quite clearly. Now, it's not uncommon for us to be asked this question: can you provide a UCV operating theatre with a layup prep room? So I'm telling you this now as ventilation safety groups, as designers, as people are getting eyes on early stage designs. These are the things that I've seen go wrong. The reason that we have an SPS prep in a UCV operating theatre is because the Royal College of Orthopaedic Surgeons say that you must lay your instruments up under the footprint of the UCV. That's fine. We can also lay our instruments up in these layup prep rooms whilst we're operating on this patient. Patient A might be in whilst we're setting up for patient B. So this arrangement may make the trust more efficient. That might be a decision that the ODPs or the IPC teams, they're the decisions that they've made. I'm an engineer. We've just got to engineer a solution for them. So in this instance, if we put a UCV theatre in and the overpressure is right there, this canopy will fail the non-entrainment test. We need to ensure that this is in a satisfactory position to overpressure into the operating theatre, and we need to consider how we're going to baffle that overpressure. So if we speak to the likes of a Preco, they'll be able to help you with that assessment and consideration. It's something that they're very familiar with. And then obviously we have other options within UK healthcare, barn theatres. Now, if you go looking for a standard layout of a barn theatre, you won't find one. There's barn theatres within the UK that are at Wrightington, Chase Farm, Poole, Leighton Hospital and Crewe have got a 2-theatre barn. There's a 2-theatre barn at Airedale Hospital up in Yorkshire. In the UK, I believe the best way to do it is to go back to case study and look at the things that have worked and look at the things that haven't. So if you're designing a barn theatre, everybody needs to be involved in the ventilation safety group, obviously, but engage those specialists who have been involved with it or had experience of building barn theatres across the UK. This is real key. If a barn theatre doesn't work, it's a disaster, and it's very difficult to get them to work once they're not working. So early stage design consideration is key. And then just for the people that may not be au fait with where I'm getting these calculations from and these figures, this is a formula that we use to work out an air change rate. Basically take the airflow in meters cubed per second, multiply it by 3,600 seconds in an hour, turn it to meters cubed per hour, divide that by the room volume, air change rate. And then we can transpose that formula to work on from the office or as a designer. We'll take a design air change rate from HTM03. We'll give the room volume. So we have two constants. That'll give us meters cubed per hour. Meters cubed per hour divided by 3,600 will give us the airflow. So then we can do things like calculate if we can make a system work, we can calculate the ductwork sizing, we can then work out the runs through the Revit models, whatever it might be. But these are the formulas that we use. And as I've already said, I'll share these slides with you so you've got it noted down in the pack once it's been distributed. So the importance of ventilation in healthcare then, why we go into this, all this effort and cost and time, what are we trying to achieve? So we're sort of moving into the sustainability argument now, but there's 3 areas that we must assess. We've got to assess natural, mixed mode and mechanical ventilation. For example, in a UCV operating theatre, you're never going to achieve the air change rate on natural ventilation. It's got to be mechanical. And there's always got to be a balance in healthcare between sustainability and what's best for the patient. So they're the things that we've got to consider. We know that ventilation is used for cross-flow ventilation to control cost control substances such as anaesthetic gases. We're going to talk about cross-flow ventilation, and that could be used in a recovery or an anaesthetic room, which is high-level supply and low-level extract. Building services engineer, obviously ventilation is used for comfort, stable temperature and relative humidity. UCV operating theatres have got to sit at a certain temperature for us to test them, so we need the ventilation system to do that. That's a good example of it. And obviously we want comfort for our end users, our patients, our staff. And then dilution is the solution, dilution of contamination. COVID-19 is a good one for everyone to tie this to because you're all familiar with COVID. But there's also viable and non-viable contamination too that we need to consider. Viable contamination is things that would multiply in free air, such as E. coli or Legionella. And non-viable contamination is things that would settle and not multiply, such as brick dust or plaster dust or lint from our clothes or whatever it might be, but that's a non-viable contaminant. Some examples of those 3 areas that we need to assess are on the slide now. So you can see that the Scope 1 emissions must be reduced by 2040. And we have an example of natural on a clinical ward there. Mixed mode is basically mechanical ventilation and a window. You may see that in offices. And then full mechanical, you've got a barn theatre on the end there that's fully mechanically ventilated space because we're trying to use that system for infection control, protecting the patient and making the staff comfortable while they're at high pressure scenarios. Cross-flow ventilation in healthcare is an example here. I've stole this image from Air Secretary. I'm sure he won't mind, but I think it gives a good example. If you think of that as the mechanical vent, the supply, high air, supply air, the patient is sitting in this position. We bathe the patient in supply air and the mechanical system removes any contamination. If you imagine the patient's exhaling anaesthetic gas in that position, the system should be able to take that away and then we'll discharge that into the atmosphere or whatever we're going to do. Low-level extracts within operating theatres are angled. So you'll remember the UCVs that I showed you before. If it's a flush canopy, if we strangle that 66%, the canopy's not going to work. So we can do things with that recirc that we need to consider. And this is a straight mechanical extract here. that we're measuring at the point of a validation. You can see we've changed our bolometer hood. We've got a shorter bolometer hood, so we can measure it at validation, and it's repeatable every time we verify it. There's other spaces that we need to consider as well. There's birthing spaces, recovery rooms, anaesthetic rooms, and they're the type of areas that we need to think about this cross-flow ventilation. Comfort and COVID-19. Comfort, like I say, operating theatres, we're always going to have a floating temperature control of 18 to 25 degrees, but when testing UCV canopies, we can't test it at 25 because the air would be too buoyant, and we can't test it at 7. We need opening windows. Natural ventilation is a mitigation tool for COVID-19, we know that. So sustainability design and future proofing. I'm just going to quickly show you an example of what the hospital of the future will look like. This is St James's Hospital up in Leeds. And you can see that this has got all the sustainability characteristics that you would expect. It's designed by WSP. It has ground source heat pumps, air source heat pumps. We've got solar PV on the roof. We capture rainwater. We're doing everything that we can with the natural environment. We have a natural ventilation facade on the building. We have sustainable methods of transport storage. So we're promoting better commuting to work and for patients. We've got a healthy environment within the hospital. But I think from my point of view, this is all well and good and this looks brilliant. But in COP26, which was in 2021, BISRIA did a presentation and they said by the time the Paris Agreement comes into force, which is 10 years after the NHS goals, 80% of the built environment that we have now will still be in use. So as designers and engineers and innovators, we need to consider how we're going to get existing facilities to work in a more sustainable fashion. And I think that's going to be a big challenge. But hopefully there's some ideas in the next couple of slides that we can take advantage of. This is a very quick overview of the NHS net zero goals that you can see on the slide here. We sit here in scope 1 for NHS facilities, but I know there's a lot of work around anaesthetic gases with desulfurane and sevoflurane gases and different types of anaesthetising patients. But we'll stick into our expertise, reducing fossil fuels and trying to get the estate facilities more efficient and working in a better fashion. You can see there's elements that are out of the NHS's control, which have a further goal put on them for 2045. So we're talking about control systems and how we're going to get the operating theatres in particular to work in a more efficient fashion. This is a snap from my dissertation work. So down the left hand side here, we just have the conditioning circuit for the BMS system, and basically it's a closed loop. It's a closed loop philosophy control system. So it's taking information, giving information back, and the bits in the middle are doing the tweaking and changing that needs to happen to make it more efficient. There's a flow chart on the right hand side of the slide there, and it's an out of hours assessment. Now this was done with the support of some clinicians down at Southmead Hospital in Bristol, and it's a philosophy that I'm also going through with Spire Healthcare as well around their UCV theatres and their appointed electrical designers and BMS consultants. So the way that we work this system is basically using a pressure transmitter. We confirm that the air handling unit's off. We could also use a TACO to do that if we've got EC fans, for example. We measure the operational room temperature, S2. Don't forget, this is an educational document. If we were doing this in reality, we would probably using S3, the low-level extract sensor, and that's why I've highlighted it, because room stat sensors are advised against in HTM. We monitor at S2 or S3 for an ambient temperature of 18 degrees. Don't forget the HVAC system's off now. And if the temperature drops below 18 degrees, we trickle the HVAC system back on, open the heating circuit, get a bit more heat into the room, achieve 18 degrees, switch back off. And we can do that in the morning until it gets to sort of 8 AM. And then we can bring the HVAC system back onto full speed, get 22 air changes back in there, and away we go in the morning. Now, this is sort of an overview of where those sensors would sit. And the reason that I've put it in is because everybody needs to be aware of S1. Like I've already told you, ignore emit S2. We use S3 for our out of hours ambient temperature. I'll put that in because it was an educational piece. But the reason that this is up here is if you think about the UCV footprints that I showed you earlier, 500 times an hour is the amount of times that the air moves between there and here, bathing the surgical site and bathing the clinical team in HEPA filtered air. So if we have the sensor there as opposed to there, the readings for the dual temperature and humidity stat will be much more accurate back to the theatre control panel, because one of the requirements of validation is that we get plus or minus 1 degree from the calibrated instrument in the center of the room to the theatre control panel, and plus or minus 5% on the relative humidity from the center of the UCV to the theatre control panel. If we have a stat there, then the offset within the BMS system is much lower, and will give you a much more accurate reading. You can see we have a standard air handling unit, and the ductwork comes up through in this fashion. As I mentioned before, 33% of the air delivered to that 500 air changes comes from the HVAC system, and we have the recirc 66% moving around in this fashion 500 times an hour, and then from the air handling unit we look for 22 air changes an hour. Now, when I put this together with the clinical team down at Southmead, this is quite interesting. So we have some data here. They have 16 UCV theatres, all ex-flows down at Southmead Hospital in Bristol. Dr. Andrew Shrippman, who's doing a PhD on this, did this data and shared this data with me. So basically, at Southmead, they have the facility to control the AHU and the UCV to off. And basically what they've done is measured the background with the UCV and the AHU off, and you can see we have a high background spike, as you'd expect. And then we bring the HVAC and the UCV system on together, and the part that was staggering for me, I thought was quite quick. You can see between that point there and that point there, within about 2 minutes, we go to a background reading of almost 0. And then he's moved his particle counter outside the square, and then you start to see these sort of spikes pick up here. The anaesthetist team down at Southmead have done tons of work on this and worked across different types of trusts. If we can get this control philosophy in, whilst maintaining 18 degrees out of hours, because if we're adjacent to, if the operating theatre is adjacent to an external space, obviously the temperature is going to drop quicker. If we can keep the 18 degrees higher, then there's a potential to put more cases through the theatre. And I think that's going to be the basis of Dr. Shrimpton's assessment and work. So how do we do that from an electrical point of view then? This is a standard configuration of a Howarth electrical connection inside our power distribution panel. And these 3 sets of connections here, HVAC running, setback and fault, are all essential. So the UCV canopy must know when the HVAC is running at full speed, and it enables us to then go into full speed and setback. But what we can do is we can take that signal and we can link it into what we call remote run. If we don't have remote run in, basically what happens is our PLC then loses a remote, it loses a run signal to all VFDs if we're using variable frequency drives, or we kill the control signal that goes to our electronically communicated fans in our bigger canopy. And what that enables is a complete shut off of the air handling unit and the UCV together, while we just monitor the ambient temperature. And then when we come in the morning, the HVAC will come on its own, and then the clinical teams will have to go to the theatre control panel and press operate, and the canopy will run up to full speed. So they're the things that are important and need to be noted. So just to give you all a bit of a conclusion to the presentation, I hope that you take the comments from BizRIA VG49 away from you and the early stages of REBA. That's important. Ductwork is a key part of the installation. DW144, 143, we need to consider those documents. Our air handling units are configured in a certain fashion for a reason, so don't deviate away from that reason. I see cooling coils on the suction side of fans. That should have been picked up at the early stages of REBA, so make sure that you follow the guidance. Health building notes and technical memorandums can tie together. We don't just pluck these numbers out of thin air. Ventilation in healthcare is there for multiple reasons. Immunosuppressed patients, patients who are sick, we need to look after our people that are working there. All the clinical people have a right to work in a healthy environment. It's there for a reason. And then net zero, I'm 36 years old, so I've got another 30 odd years of this. And I think this will be the biggest challenge of my career. Again, something I'm massively passionate about. That's why I did my whole entire dissertation on whether the healthcare system in the UK had achieved net zero. But I think it'll be the biggest challenge. So thank you for your time. I do hope you found it of use. There's a survey link there. Everything in this presentation today has been done by the survey that we did last March. If you could just take the time out to follow that survey, I'd really, really appreciate your feedback. It'll take you 2 minutes. And on the other side there's a link for my LinkedIn. If you wish to connect with me, discuss with me, my email address is there. Please, collaboration and discussion is the only way that we can upskill the way that things are going in the UK. So please do reach out and get in touch with me. Thank you.
Thank you very much, Mike, for a very detailed, typically detailed presentation. Those who've heard you present before will know that is a characteristic of when you do these webinars. As you'd expect, given the depth of the presentation and the technical matter discussed, we haven't had a number of questions. And I wondered if I could kick off by asking you a few. One of the first is, with Wilson flow grids, what is your view on whether these need any maintenance or recalibration during their life? Absolutely,
yeah, and that should be picked up early in the stages of REBA. So some of the scenarios where I've seen Wilson flow grids suggested is, if you remember the layout that I showed you of the UCB operating theatre that was symmetrical, there wouldn't be a way to get a traverse on those legs because the ductwork arrangement was too tight. So we'd do that under an indicated reading. Now, previously on other projects I've seen that suggested that we would put Wilson flow grids within that system and that would give a readout back to us. In my opinion, if you can't get in there and take a traverse and make sure that it's back to a calibrated instrument such as a micromanometer, then I would find it very, if a patient was sticking that theatre post handover, the first thing we would go to is, right, what's the dilution air change rate in there? And for the last 5 years, it might have been, well, we've been checking this Wilson flow grid. If you've been checking a Wilson flow grid and it's not been calibrated, then I think it would be very difficult to have that argument. So yeah, I think you've got to calibrate it. It's got to be repeatable, and it's got to be defined at the early stages of REBA how you're going to do that.
Thank you. Another audience member has said, when validating a system, how does Howarth ensure that the air handling unit is compliant with HTMO 301 Part A, Chapter 9, given that there are 230 clauses stroke requirements, which obviously is quite a number.
Yeah, it's there's a lot in there. So basically what we do at validation, if we the first thing we do is be involved from the start if we can. So we'll go through and we'll make sure that everybody's familiar with the scope of works and what's required of that system. That's the first thing. The second thing when we get to site is we'll run an Appendix 1 and 2 check. That's the fabric and the standard check that would be carried out at the annual verification of the system, which is a requirement. That's in HTML3 Part B. You go to the back of that document, there's appendices in there. Look through that appendices. Now, in the last 12 months, what we've done is we've gone belt and braces on that again, particularly on validations. So if you go to HTML3 Part B, look at Chapter 3, there's, I think it's 140 questions about the air handling unit, its environment, the plant room. They're the minimum standards, and that was a recommendation that was given to us by an authorised engineer for vendor. And obviously, when we were told that, we were thinking, oh my God, another 140 questions that we need to do. However, it's proved really, really good for us in validation, because validation in HTM, it isn't a snagging exercise. It's an exercise to check that the system has been correctly commissioned, designed, installed, and it's fit for clinical use. However, I use it as a snagging exercise to start a conversation with the main contractor or the installer of the air handling unit. And the Chapter 3 checklist is a really good thing that helps me collate that snagging list at the front of the document. So at the front of the document, I might put things like the fog coil is incorrectly installed, for example. It might be finned, for example. We'll put that in there. That's a non-compliant. So then you start knocking it down. And from a validator's point of view, it just starts to help you put the blocks together, because there's such a vast array of things that a validator needs to consider. Chapter 3 checklist really, really helps. And we've made that electronic as well. So we'll do it electronic, we'll take pictures. It's almost like another checklist for us. So yeah, that'd be my advice, Chapter 3.
Thank you. Another attendee's asked, when installing, commissioning and validating a barn theatre, and that was an area you focused on, how many combination of grids and entrainment tests should the manufacturers commissioning company and validators carry out, and should it differentiate between the various teams?
Yeah, so yeah, it should. So I think from a manufacturer's point of view, I think once the manufacturer has proven that each UCV achieves the minimum requirements that are laid out in Chapter 12 of Part A, acceptable. But then I think it's the validator's responsibility then to put a scope of works together that says at validation we are going to do this many variations of testing. And if there's that many variations of testing, and it is a lot of testing when you do a barn, if it's a four UCV barn, it is tons of testing, because you have to test in the different scenarios. So let's call it pod 1, 2, 3, 4. We switch pod 1 off, we test 2, 3, 4, and it's grids and entrainment. We bring pod 1 back on, switch pod 2 off, pod 3, pod 4, we test 1, 3, 4, grids and entrainment. It's a lot of extra work and a lot of extra testing. So I think from a validator's point of view, initially from a manufacturer's point of view, prove that the canopies are working and prove that you're getting the right flow rates and the entrainment's fine and the airflow strategy within the barn is correct. Then as part of the validation cause and effect testing, that has to be done by the validator, and it may be done with the support of the manufacturer, but that would have to be done as an extra, I would suggest.
Thank you. This is on an associated matter. What would a typical control strategy be in a barn theatre?
So the barn theatre control strategy can be quite complex and quite in depth. So thinking about the ones that I've been involved with, 4 UCVs, four AHUs that are attached to each UCV. So if one AHU goes down, we still achieve at the time it was 75% of the flow rate, 75% of the pressures. And then the way that they worked out the temperature scaling and the banding, they sort of took an average across the barn and then used it, trimmed it in across those air handling units that were attached to those AHUs. Each UCV had its own UCV canopy and UCV and temperature set point, but it was very, very complex and had to be considered again at validation.
Thank you. Another attendee's asked, I think you referred to this, what manufacturer was the sustainable, in inverted commas, AHU from, please? Did you mention?
Yeah, so the one with the heat pump on. I'm not 100% certain because Siggy brought that with me to me. But I'm sure that if you went to the likes of Mansfield Pollard or AHS or one of the big UK manufacturers, I'm sure that they would be able to provide something similar, because that's just naturally the way that the industry is moving. Yeah, I'm not sure on the manufacturer. It looked like it was European, to be honest with you. But I'm sure that it's something that a UK manufacturer will be able to provide with little issue.
Somebody else has asked, what's your opinion on the findings of the Scottish Hospital inquiry and thermal wheels for heat recovery?
I must admit, I'm not massively au fait with the report that's been put together, but one thing I would comment on is I know that Howarth have been involved with a lot of projects up in Scotland, and I know that a lot of the air handling units supplied from supplying the UCVs have got thermal wheels on. And then if I take a cross-reference of the country, it seems like a predominant number of the thermal wheels seem to be north of the border. But I'm not sure of the study. I'll have to go away and read that and understand it. Sorry.
Fair enough. What's your experience regarding putting the AHU and UCV into setback mode? Another person has asked. It's a critical way to achieve low overall energy usage. How do you typically see any issues with this approach regaining pressures or temperatures, etc., when returning to standard operational mode?
Yeah. No, I don't, and I've really encouraged people on the call, if they've got responsibility over a site to do that, then go and do it. Run it by your authorising engineer for them. It's been a recommendation within HTM for a while now, since 2021, but it's been a thing that we've spoken about in healthcare for a long time. And when I did my dissertation, I actually went to site, and I'd be happy to share this data with people. I went to site, I put data loggers onto equipment, and I actually calculated the amount of energy that was saved. Like I said in the presentation, sustainability and reducing consumption in healthcare is the biggest challenge, particularly when it comes to HVAC systems, which is the most energy hungry piece of kit as engineers we're probably going to deal with. So if we can reduce the load by switching it off in the evening, along with the UCV and the AHU together through that electrical interlock that I showed you, and then we monitor the out of hours to make sure that it doesn't drop below 18 degrees. So the guys at Southmead who've done the research, that was one of the considerations that they overlooked. The guidance is there in HTM. What I've shown you today is just the process of how you can implement it. And we can't let it drop below 18 degrees. And we know that within a couple of minutes, the dilution, as far as they were clinically concerned, and I'm not a clinical person, but the dilution within the space was back up to a level where they believe they can start to increase the throughput. But even if you can't do that, and you're still going to do 30 minutes in the morning to let the room purge and get back up to speed, brilliant. We've saved 10 hours of electricity from the UCV and the AHU throughout the night, or 12 hours through the night. So we've got to have the control strategy. We've got to have a robust control strategy. We've got to have a BMS system that's reliable, and most importantly, we've got to have a theatre control panel that's reliable as well, because there's a lot of theatre control panels that are inadequately commissioned, not correctly validated, indicate inaccurately. This is all part of the validation. We validators have to stop this happening. So if you're doing it in an existing estate, sort of professional advice, almost get a recommission, and go from there. But you will save so much energy. I really recommend that you do it.
Thanks, Mike. Somebody else has said validation of barns now clear. I assume the range of tests would be similar in complexity on annual validation.
So that scenario then is up to the ventilation safety group and the IPC people. So if they want to run through that annually and do that cause and effect testing in that instance, then it's up to them. Obviously, you're going to have to shut your barn for a longer period of time and consider that extra time that you're going to have on site. Personally, from me, if you've proved at validation that with the barn design that the canopies contain and protect the patient, if one pod trips, we still achieve the room pressures, we still achieve the dilution air change rate to a percentage that's acceptable to HTM, I would just go through the servicing of the UCVs as you would service a normal operating theatre to control the capital cost on that one, and then maybe every couple of years go back and do that cause and effect. But if you've done it at day dot, in my opinion, it would be a waste of money. But your authorising engineer may see that different, your ventilation safety group may see that different. That's just literally my opinion.
No doubt conscious of costs and carbon savings. Some trusts are switching off theatre ventilation at night, one attendee says, and asks, can your canopies be turned off safely or should they remain in background mode?
No, we can turn the canopy off. One thing that you need to be careful of if you're leaving the UCV on and switching the HVAC system off is that heat gain that I spoke about. We have a heat gain that's coming from the canopy. And with no HVAC in there, you're going to really push the temperatures up inside the operating theatres. Potentially, the operating theatre temperature in the morning could be too warm. So, no, the canopies can go off. What I'm working with Spire Healthcare now across all of their UCV theatres and their appointed BMS contractors is a strategy to do that. And we're looking at, obviously I work for Haworth, but we can work with any type of control system. My background is electrical engineering, so we can look at different types of control systems, time with the BMS engineer, make sure that it's intelligent enough to do what we need it to do, make sure that we know that it's going to come back on in the morning, make sure that we're not putting too much strain on it. Some of these systems have got single phase motors in, we need to think about transformers coming back on. We've got different types of inverters. Is there a risk that the inverter could trip on ramp up? The last thing we want is for someone to have their operation cancelled 30 minutes before they go in because of our control strategy. So it's important that it's robust, but it can be switched off, and I would advise that you do switch it off, particularly if you've got the AHU going off as well.
Thanks. Another attendee said one item that HTM03 doesn't appear to be clear upon is the ductwork leakage. Is the HTM inferring that for low pressure systems, the system should still be installed and tested to Class B?
Off the top of my head, I must admit I thought it was referenced in HTM in Part A. I may be wrong, but again, if we're going through those early stages of REBRA and you've got competent people that are being involved with it, then they would pick that up in the early stages. I've seen existing or new projects where we've got to the final handover and only the supply system has been pressure tested and then it had an existing duct working, then the existing ductwork, the authorising engineer wouldn't accept that. The existing ductwork was pressure tested, it failed everywhere and just become a big contractual nightmare. So I must admit, I thought the pressure testing was noted within HTM, but it's a requirement of building regulations. There's published data there by BESA. It's all there. It's just up to the competent people to pull it all together and make sure we're ticking all the boxes, really, to make sure that, most importantly, the NHS is, or the private healthcare sector, whatever it is getting what they've paid for. So yeah, that's all I can say really on that.
Okay, somebody else has said, not a question, just a thank you for the presentation. The person in question says, I'm currently working on an undergraduate assignment on NHS Wales decarbonisation net zero, and the presentation has provided me with a lot of useful information. So thank you there.
You're welcome.
Just moving on to some further questions. I've had one that says, is 80% backup of air supply if an AHU fails a requirement for HTM compliance or a nice to have?
No, that's a requirement. So it is referenced within HTM Part A. One thing that I've not actually discussed today is the volumes that we look for. So one of the frequent failures is the volumes of terminals. So at validation, all designs must be at design plus 10%. That's a requirement. If it's at 120%, we fail it. We don't go to site, we say rebalance the system. The 80% comes from, there's a design requirement in there for the air handling unit. And then there's also a requirement or an allowable, there's a bit of wriggle room, a bit of elbow room in HTML3 Part B for verification. So when we go back in an annual event, we're allowed to provide 80% of the flow rates that were given in Part A. So we can drop the air change rate down and we can still be compliant. That's the same with the room pressures, but we can't apply those 80% rules to the UCD canopy testing, for example. That's black and white, it's either passing or failing. And I would be very careful about applying those 80% values in spaces such as isolation rooms or pharmacies. But again, your ventilation safety group, your authorising engineer, they're the people there to protect you from these types of things. So it's not nice to have, it is an essential. And again, it can all be captured at the point of design, right at the start of the process.
We've still got a few more, some interesting questions. Somebody's asked, HTM guidance suggests that ventilation in theatres continues to run in the event of fire condition. It says duct smoke sensor shuts off if required. And then has asked, how do you anticipate the fire damper in the slab will be operated to ensure triggering by fire alarms does not disrupt the desired continued airflow?
Yeah, so another thing that I didn't mention within the presentation is fire strategy. So when we do the validation, we take a look at the fire strategy, we look at the fire commissioning documents for the SFDs, for the smoke fire dampers. Various trusts look at this differently, and again, the scope and the specification is written by the authorising engineer for vent around fire strategy. We literally just make note of it within our reports, and we don't do a full in-depth detail assessment of the smoke fire damper strategy because it's not massively our experience really. We can check a damper, check that it closes, check that it opens. That's obviously fine. But in terms of looking at the strategy and everything, that's something that I would recommend that they just discuss with their authorising engineer for that particular site that they're working with or are managed by. I think that would be the safest bet.
Thank you. The next question is, how airtight do these spaces have to be? How often are airtightness tests conducted, and what methods are used to test for airtightness?
So permeability testing of the room is, like I said in the presentation, something that's being looked at the moment by the SVH Society, which is the Specialist Ventilation and Healthcare Society, a collection of all the authorising engineers from them, or most of them in the country, and the CIBSE Healthcare Group, I'm sure we'll be looking at in their design guide. One thing that Malcolm Thomas says, who wrote HTM, who was the author of it, doesn't want it. These rooms need to bleed pressure. We need to have pressure moving in the right direction. But I think what he's coming from, well, where he's coming from when he's talking about permeability testing is we just need to know where that pressure is going. So we've got adequately sized pressure stabilizers in the room. We can have leakage across the door gaps, and we've got smoke fire seals on the doors. Is that considered in the pressure stabilizer calculation? So they don't have to be submarines by any extent, but they've got to be able to withhold the pressure, and we've got to understand where the pressure is moving when we come to do the commissioning and the validation. If there is any designers on the call, at the back of HTML3, there's an appendix about calculating movement of air pressure stabilizers and stuff like that. But again, I mentioned a Preco in the presentation. If you ever have an issue with pressure stabilizers, I'll speak to a Preco. But yeah, I think that's probably the comment on that. It doesn't need to be a submarine, but we need to get it passing to that criteria, 2.5 meters squared per meter cube per hour, at 50 pascals, positive and negative.
There's one or two other questions. Somebody's asked, in terms of UCV systems, is there any use in taking static pressures adjacent to UCV recirculation fans when balancing a system?
So you've got to be careful with UCV canopies. So there's inside the canopy, there's obviously a recirculation fan. The recirculation fan is in series with the AHU fan. So the AHU fan is pushing volume down the air handling unit, and then the UCV is snatching that volume and it's pushing it over the HEPA filters. So if you were to drill a couple of holes within a duct close to the fan, 500 mil from the fan, a meter from the fan, 1.5 meters from the fan, you would see a significantly negative pressure by the fan. So there's no point in drilling a test point there. You would then, as you move forward, the pressure from the air handling unit system that will overcome the recirculation facts of the UCV canopy, and you'll start to go positive again within that ductwork as you'd expect, because you've got these two fans sat in series. So in terms of testing the UCV canopy, get the test point as far away from the UCV as you can, and then if you can get a test position close to the UCV fan, but far enough away that it's under positive pressure, and replicate that on the 4 fans, like I showed you on the one that dropped from the ceiling. That was the perfect arrangement. That's adequate.
Thank you. Another question, can Howarth help with the technical review of systems at the early stages of REBA?
Yeah, so we have chartered engineers that work at Howarth. Obviously, I can help with design reviews within that team, and that's something that we frequently do. We try to work as a trusted advisor almost within the chain of command. In that early stages of REBA, in that sort of stage 0 part of REBA, that's where you need to get involved with the likes of Howarth, so we can get our hands on the design, make comment, make some design changes with the support of the mechanical engineers, whoever that might be, and go from there. But yeah, that's certainly something that Howarth and our projects team can do.
Thank you. Somebody else has asked, theatre staff use UCV canopies in setback for conventional operations. Is there anything that should be considered with regards to airflow across the surgical site?
Yes. So one of the requirements now that's always been in HTM, I think it was in the 2007 version, is that when a UCV canopy drops from full speed to setback from orthopedic to conventional, however you want to word it, when the arrows go from green to amber, we need to achieve between 0.2 and 0.3 meters a second at the bed. Now, the way that it explains it is really sketchy and it's not very clear. But I've recently worked with an authorising engineer on this, and we've just took the 4 readings in a 6x6 grid, but we measured the full 6x6 grid with the canopy and setback on an X-Flow 28, and all of them achieved greater than 0.2, and maybe 1 or 2 are above 0.3, about 0.33. So I would deem that acceptable. So when it's dropping to setback, that's something that should be checked at validation. And if it's checked at validation, I don't necessarily think it needs to be checked at the annual verification. It's certainly something that we don't do at Howarth, but we could do if it needed to be done. It's only a 30-minute test, but yeah, there is a velocity that needs to be thought of when that canopy drops to setback.
Somebody else has asked a couple of last questions. To what extent can Howarth help in terms of refurbishment of an operating theatre?
Again, yeah, Howarth, that's something that Howarth can do, as well as assessing the design. We can do what we call turnkey projects. We're doing one at Weymouth at the moment, and we've done a number of them over the years since even back when I was a commissioning engineer. I go around doing commissioning refurbishment type jobs. So yeah, everything can be considered and taken account of within reason, obviously. by our operations department and our supply chain. So yeah, that's something that we can do.
And one other Howarth related question, do all Howarth control panels have the electrical connections that you showed at the end of the presentation?
Yeah, so I'd say 80% of them do. There's some really old canopies out there, like I said earlier, they're on transformers, single phase, and for those ones that are knocking about, I have a design solution for getting them to switch off out of hours. I must admit we've not implemented that yet, but we're going to have to implement it at some of the sites working with these BMS contractors that we've got on projects coming up. But in that instance, there's ways that we can get around it by installing additional contactors or working in a fashion that we may be able to change the transformers to drives and then work the drive off. There's different things that we can do from an electrical engineering point of view, but certainly all newer type systems have that arrangement in.
Thank you very much, Mike. I think that concludes the questions we've got. There were a fair range of them, and credit to you that you're able to answer them. I'm sure if other people have questions who've been on the webinar, if they address them to you, you'll do your best to answer them. Just to say thank you very much for presenting so well today and for answering the questions. And I know that Howarth is very keen that people click on the QR code with any feedback they have. So that would be great. The other question we've had from one or two is, will the slides be available and shared after the event? The answer is yes to that. So thank you for all the people who attended today, and particularly thank you to Mike for a very interesting presentation. We hope everybody found it useful. Thank you.
Thank you, Joey. Thank you. Bye, everyone.
Bye-bye.